Okay, I'm going to get started. Hope you can hear me clearly. Last couple of weeks, we've been discussing light, the nature of light. Beginning today and on Thursday's class, we're going to move on to discussing the topic of relativity, Einstein's relativity. And then beginning next Tuesday, we're going to be talking about quantum physics and the nature of electrons and photons and subatomic particles. And those are the last two topics in the course, last two topics of the semester. So in the syllabus, you see that here. Here we are beginning relativity. Today and Thursday. Here we are beginning quantum physics next Tuesday, Thursday, and the following Tuesday. Okay, so let me go to my slides for today's class, if I can do that. And so here's the content for today. I'm going to start by talking about the foundations or the bases of Einstein's relativity. And there are two foundations that we're going to talk about. One is what we call the invariance of the laws of physics, and I'll explain that. And then the second one is what we call the invariance of the speed of light, and I'll explain that one. But these two postulates are the foundations of Einstein's relativity. We'll then talk about two of the key consequences of Einstein's theory of relativity. So one of them that is contrary to everyday notions, to common sense, is what's called time dilation. In everyday common sense notions are that the duration of events, or time interval of events, would be agreed on by all observers. In relativity, that's not true. And so that's an important consequence of special relativity. The second one has to do with length contraction. And again, that's at odds with our sort of everyday notions or our common sense notions. And that's that everybody agrees on the length of objects. And that's not true in relativity too. And so these phenomena of time dilation and length contraction emerge from those foundations of invariance of laws of physics, invariance of speed of light, and we're going to explore those. And then finally, in today's class, I'm going to make a few comments about what this change in the fabric of space-time does for Newton's laws of motion. And we'll discuss further in the next class what that change in the fabric of space-time did for Newton's laws of motion. So this is the plan. So one thing that's interesting about relativity, one thing I kind of like about relativity, is that whilst it's a dramatic change in how we think about space and time, that sort of background on which the laws of physics play out, it didn't require any complicated mathematics. Actually, Einstein changed our understanding of space-time with just some basic high school mathematics. And so we've all had years ago the mathematics that we need to revolutionize our notions about space-time. It's just that it makes space-time such a bizarre and strange background in which the laws of physics play out. The laws of physics determine how things work. So that's interesting. And to talk about this space-time, we first got to introduce a concept that we have mentioned before in 211, but I'm going to mention again here in 213, and it's called reference frames. And specifically, I'm going to talk about inertial reference frames. So reference frames you've met before. I might have mentioned the word inertial reference frames before. We'll make it a bit more concrete this time. Okay, so what are reference frames? I'm trying to show you in this little sketch what are reference frames. So reference frames are coordinate systems. Reference frames are spatial and time coordinate systems. So in three-dimensional space-time, we have three space coordinates. We normally call them x, y, and z, and we have a time coordinate t. And if you specify the x and y and z space coordinate of something and its time coordinate, so if you specify x, y, z, and t, you have located that something exactly, precisely in space-time. And so that's what we mean by a reference frame, a way of locating, a scheme for locating, you know, this or that occurrence, this or that event in space-time. So on this slide, I've showed two reference frames, because showing two reference frames is going to be key to understanding Einstein's relativity. So the two reference frames I'm thinking of, look, I've got a picture of a train passing through a station here. That was an accident that I put a picture of a train passing through a station. It was important. I'm going to think of one reference frame as being the reference frame of this passenger on the platform. And so that's an example of a reference frame. The reference frame is locked to, at rest in that, on that platform. And then I think of a second reference frame, passenger on the train. Here's the passenger sitting on the train. And that's a second reference frame that's locked to that moving train. And so I've pictured those two reference frames here. I've called frame S the one that's locked to the platform. And I've called frame S prime the one that's locked to the train. And each of these reference frames, you know, has spatial coordinates to represent spatial positions of objects or events or occurrences, and a time coordinate to represent the time coordinate of objects, events, or occurrences. In the S frame, the platform frame, I just called them X and T. And I'm just drawing one space coordinate, because it just gets complicated to draw three space coordinates. But it is a reference frame in three-dimensional space plus one-dimensional time. And then I've done the same thing for the train reference frame. There's a spatial coordinate called X prime for the train, and there's a time coordinate T prime. And we would use those to locate the positions in space and time of objects or occurrences or events. And importantly, right, if you're in the platform reference frame, so supposing you're the platform observer here on the right, then you see the train reference frame is moving by you. You're at rest in the platform reference frame. But if you're in the train, Okay, now I'm in the train here. I see the platform reference frame as moving by me. And actually, if the platform observer sees the train reference frame moving by at speed v, then the train reference frame observer sees the platform reference frame as moving by at speed v in opposite directions. And so that's an important concept, these different reference frames. And both reference frames are perfectly valid. We'll see that both reference frames are perfectly valid. The platform reference frame is not some sort of privileged super reference frame. The train reference frame is not some privileged super reference frame. They're both equally valid reference frames. Okay, so now I want to talk about the foundations of relativity. We've introduced the concept of the reference frames. And as I say, there's two of them. One is invariance of laws of physics, and two, that's invariance of speed of light. And I thought I'd show you this little cartoon because I kind of like it, because in relativity is all about understanding in physics what things are relative and what things are absolute or invariant. What things different observers can see as different and what things different observers always see as the same. So that's really what relativity is about. That's the key to relativity. And in this little cartoon, right, our two friends here are arguing about the number on the ground, and one is arguing that it's 6 and one is arguing that it's 9, and so they're seeing that same object as different, a 6 or a 9. So that would be something that's relative to them. They have different beliefs, opinions of what that number is. But an example of something that would be agreed on by them is that 6 plus 9 is 15. They would both agree that 6 plus 9 is 15. So in that example of everyday life, you can see how some things are relative to us and some things are absolute to us. Look, I was thinking of another example of this. This is maybe not very tactful, but think about the washing up, right? Now, when I think about the washing up, I think, well, I think I do a fair amount of the washing up at home. And then, when my spouse thinks about the washing up, she's thinking that I haven't done the washing up for 35 years. So that's something that's relative. We've got different opinions on how often I do the washing up, different perspectives on that. However, we both agree that the washing up gets done. So that's another example, not a good one perhaps, another example that some things are absolute and some things are relative. I just see in chat, is there a reason that the lecture quiz is due to 1:15? Well, the lecture quizzes I do whenever I get to them, I guess. Did I actually publish it? Is that the reason that it's... There's no reason to that, and I don't know it's going to be 1:15. It's whenever I get to it. So I hope that's not become confusing. Okay. So let's talk about, I talked about relativity and absoluteness in everyday life a little bit. Let's talk about relativity and absoluteness in physics problems. So I'm going to show you 2 slides here that are examples of some things that are relative and some things are absolute. So in this slide, take a look at this. This is something from 211. Here I am in a truck, or here I am in the back of the truck, and I throw a ball into the air It goes straight up into the air, and then it falls straight back down. I catch it. So this is a motion. This is a sketch of motion of a ball, importantly from the perspective from the perspective of a passenger in the truck, where the ball goes straight up and comes straight down. And so that straight up and straight down motion of the ball is actually something we'll see that's relative to the observer. But in understanding the ball's motion, in understanding the ball's flight upwards and then back downwards, that's determined by the laws of physics. It's determined by the fact that there's a gravitational force on the ball, and that gravitational force on the ball creates an acceleration of the ball according to Newton's laws of motion. And that, we'll see, is agreed on by all observers. So this little slide here is a nice example in thinking about the up-down motion of the ball when thrown from a truck. Is a nice example of some things we're going to see that are relative for physics observers. The ball's straight line up-down motion is relative. And some things that are absolute. The laws of physics, force of gravity, Newton's laws governing the motion of the ball, they're agreed on by all observers. Okay, so here's the same thing, but viewed from a different reference frame. This is viewed from a pedestrian's reference frame as I on the back of the truck fly by, throwing the ball into the air. In this reference frame, the ball's motion is not simply up and then down. The ball's motion is like a projectile motion. It starts over there on the, over here on the bottom left. Ball heads upwards on a curved parabolic path and is caught over here on the bottom right. So that's a different motion, a different path in that reference frame. But the pedestrian observer also agrees on the laws of physics that determine the ball's path. That pedestrian observer also agrees that motion was due to the force of gravity that was acting on the ball, and also agrees that force of gravity created an acceleration of the ball that was determined by the force and the ball's mass, the ball's inertia. And so that too is an example of some things being relative and some things being absolute. Here, the laws of physics are absolute. So one of the key ingredients in relativity is that the laws of physics are absolute. They're the same in the truck reference frame, the passenger reference frame, as they are in the pedestrian's reference frame. So that actually has some important implications. And I just got a slide or two to stress these important implications in relativity. So look, here's a train on the tracks. And inside one of these boxcars, Baxter has got stuck in a boxcar. And there's no windows in the boxcar. The door's not open on the boxcar. And Baxter's wondering whether the train is moving or the train is not moving. And you can't tell. The laws of physics can't tell you whether the train is moving or not moving. So Baxter couldn't throw a ball into the air and catch it and try and determine whether the train is moving or not moving. And so that's an important aspect, consequence of relativity. There's no special reference frame that's at rest and others move with respect to it. And there's no way whether you can tell your reference frame is at rest and others are moving with respect to it, or vice versa. So that there is no special at-rest reference frame. All reference frames moving with respect to one another, all inertial reference frames are perfectly valid reference frames. Here would be another example. This is when I lost Baxter in a FedEx plane. So Baxter's flying through the FedEx plane, and he's inside the cargo hold of the FedEx plane. There's no windows in a FedEx plane. And he's wondering whether he's at rest or he's moving in the FedEx plane. And again, he can't use the laws of physics to determine whether he's in motion or at rest. He can throw a ball in the air and catch it, and he can't distinguish whether he's in motion or he's at rest. So it's a second example of there's no privileged at-rest reference frame in relativity. You cannot tell whether you're at rest or in constant motion. Okay, so that's the laws of physics being absolute is one key ingredient of relativity. And here comes the second one. And the second one is the one that's at odds with our common sense. And so because it's at odds with our common sense, I'm going to give you an illustration of what our common sense is first. So speed of sound waves, producing some sound waves over here on the left-hand side, and I'm listening to them in my car in the center here, or my car on the right here. The speed of the sound waves depends on your reference frame. So if you drive towards the loudspeaker, the sound waves are approaching you faster. If you drive away from the loudspeaker, the sound waves are approaching you more slowly. So the speed of sound, and this kind of makes common sense, this seems like natural or normal, depends on your motion through the air. But in relativity, the speed of light is quite different. The speed of light is the same in all frames of reference. So the analogy of the car driving to or from the loudspeaker for light is we got a flashlight now over here on the left-hand side, and I'm in a space rocket or spaceship, and I'm traveling towards the flashlight, or I'm traveling away from the flashlight at high speeds. But still, in relativistic space-time, you actually measure exactly the same speed of the light rays approaching you when you travel towards the flashlight as you would as when you're receding, traveling away from the flashlight. It's quite unlike the case of the sound waves. And so that's the second ingredient in relativity, that the speed of light is also invariant. So let's step back at that moment, this moment, and just quickly review that, because it's sort of important to our understanding that, as I say, in everyday life, I've dropped my pen, I'm going away. Everyday life, there's some things that are absolute and some things are relative. You know, how often I or my partner thinks I do the washing up. It's relative to our own perspectives. But the washing up did get done. That's absolute. In physics, in relativity, the things that are absolute are the laws of physics, say law of gravity, Newton's laws, and that the speed of light is constant, absolute for all observers. Things that are relative are, well, look, that, you know, when I was in a truck, I thought the ball went straight up and straight down, straight line motion. When I was a pedestrian, I thought the ball went in a parabolic path, a curved path. So that was obviously relative. One of the puzzling things about the constancy, the absoluteness of the speed of light is the following. How can the speed of light be constant? So the speed of light, here we are. The speed of light, like any speed, you could measure by measuring the distance traveled by the light and dividing it by the time that the light took to take that journey. So we could apply this formula from physics 211 to calculating the speed of light. Just take the distance traveled and divide it by the elapsed time. And different observers could do that. Different observers in different spaceships, or different observers in the train or in on the platform could do that. How could they all come up with the same number? How can they all come up with 3 times 10 to the 8 meters per second? The only way they can come up with the same number, 3 times 10 to the 8 meters per second, is if we change our understanding, we order our notions of distance and time, these quantities on the left-hand side, on the right-hand side. And so what I was going to say Isaac Einstein then, what Albert Einstein did in order to have the laws of physics be constant in all reference frames, and in order to have the speed of light be constant in all reference frames, he had to change everyday notions about space and time, specifically everyday notions about distances or lengths of objects, and about intervals in time, about durations between events. And so we're going to see what he did to space and time. Okay, so Einstein modified our notions of space and time. And so we're going to look at that. There's going to be a new geometry of space and time. And this slide kind of summarized what he had to do. So I'm not going to go through all the algebra of what he did, but this slide will give you an idea of what he had to do. So in this slide, you're seeing a light ray over here on the left-hand side from this flashlight over here on the left-hand side. And you're seeing 2 observers. There's this observer here in this space rocket, and there's this observer in this space rocket. And the observer in the left-hand space rocket traveling towards the flashlight. The observer in the right-hand space rocket, say, traveling away from the flashlight. Now, each of those observers has a reference frame, like the person on the platform and the person in the train had a reference frame. And so here I've denoted the reference frame of the left-hand observer. I called it the unprimed reference frame. And its spatial coordinates are x, or spatial distances would be delta x, and its time coordinates, they're t, or time intervals would be delta t. So this is how we're going to, with the x's and t's, the unprimed x's and t's, we're going to label that observer's reference frame. And then similarly over here on the right, this is the second observer's reference frame. And we're going to label their spatial coordinates x prime, their time coordinates t prime. If they measure lengths, they're going to be delta x primes. Measure time intervals, that's delta t primes. And so that's the prime reference frame. Now, if they want to measure the speed of a light ray, the way they would measure the speed of the light ray is let's measure 2 events. When the light ray from the flashlight passes this first flag, and when the light ray passes this second flag. So we could measure the time interval from flag 1 to flag 2. And we could measure the spatial distance from flag 1 to flag 2. So they can both do that. And if they measure the time intervals and they measure the spatial distances, then they've just got to take distance over time to calculate the speed. And so that's what they're going to do to measure the speed of the light ray. And so in the unprimed reference frame, we measure a distance delta x between passing the two flags and a time delta t. And in the prime reference frame, that observer measures a distance delta x prime and a time interval delta t prime. And then when the unprimed observer wants to calculate the speed of light, they're just going to take their delta x, that distance traveled, divided by that elapsed time. And they're going to get 3 times 10 to the 8 meters per second. And the same thing for the prime reference frame. When they calculate the speed of light, they're just going to take their measured distance between the flags and their elapsed time between the light passing the two flags, divide them, and they're going to get 3 times 10 to the 8 meters per second. And the key thing that Einstein had to do to what I would now call classical space-time, the old-fashioned Newtonian space-time, he had to modify that to invent a new relativistic space-time to accommodate the absolute speed of light. Specifically, what he had to do was modify our notions of these spatial distances and at time intervals. And in particular, these two observers are not going to agree on the time intervals between the two flags. And in old-fashioned classical Newtonian Galilean space-time, two observers would always agree on the time intervals, the durations between passing the two flags. But in relativistic space-time, then the two observers don't agree on the time intervals. In that way, you can come up with a new space-time, a relativistic space-time, in which the speed of light is always the same value. The speed of light is always a constant. And so let's explore the results of that. I now know what the problem with my quiz was. I guess I'd already published it. So well, let's deal with that when I get to the quiz. So that was my mistake. Okay, so I want to talk about time dilation, which changes our notion of time intervals. And then I'm going to talk about length contraction. So time dilation, let's start with that one first. And this is a key ingredient in relativistic space-time. So in time dilation, I'm asking you to imagine two observers. So here are the two observers. There's one who's on the platform and one who's in the train. So in green here is the observer on the platform, and in orange here is the one that's in the train. And this sketch here is from the perspective, if you think about this sketch, it's from the perspective of the observer on the platform. The observer on the platform has seen the observer on the train move by at speed v. And the observer on the platform has their reference frame. It's an unprimed reference frame. The observer on the train has their reference frame. It's the prime reference frame. And they're both looking at the clock that's on the platform. So they're both looking at this this clock here. Now, the observer on the platform sees the clock is at rest. The observer on the train sees the clock is in motion. And they actually see, imagine a second ticking by, or a hour ticking by. They see different intervals of time for that second ticking by, or that durations of time for that second ticking by, or that hour ticking by. And here's the equation in relativistic space-time. Here's the equation that describes that. So the observer on the platform looking at the platform clock sees the correct time, what we call the proper time. That's the t here, and it's the t here over on the right-hand side of the equation. The observer on the train that's seeing a moving clock sees a dilated time, and that's the t prime here. That's the orange t here. And those two times are related by this formula here. This is the time dilation equation. And this formula, you see, it involves this piece that changes the proper time into the dilated time. It's this division by the square root of 1 minus v squared over c squared. And that factor of 1 minus v squared over c squared, it's given a special name. It's called the Lorentz factor. And that factor would be 1 if the train was at rest in the platform. And it gets bigger than 1 if the train is moving through the station. Is it motion with respect to the platform? And that's time dilation. That's that the ticks of the ticks of the clock on the platform starts to stretch out when observed from the moving train. And the faster the train is moving, the more they will stretch out. And that's time dilation. Now, time dilation works actually the other way around too. So here's the partner time dilation. Now, so in this sketch, again, I'm picturing the observer on the platform and the observer in the train. So the green and the orange observer. And again, I'm imagining their reference frames, this unprimed reference frame and this prime reference frame, in the platform and the train respectively. But now we're looking at the clock in the train. So this clock in the train is at rest to the train observer, but it's moving for the platform observer. And here's the motion of the platform observer with respect to the train's reference frame. So this is a picture now with respect to the train's reference frame. So the intervals of the clock. So imagine 1 second of ticking by on the clock in the train, or 1 hour ticking by in the train clock. The observer on the platform sees those 1 second, 1 hour intervals as lasting longer, measures them as lasting longer. And again, this equation down here that describes time dilation describes that stretching of the time when you observe a moving clock. So in this equation now, see T prime, this is the time measured by the train observer for the train clock. So that's where the train clock is, that person sees this train clock as stationary. They see the proper time. The observer on the platform sees a stretched, a dilated time for the seconds ticking by the clock, or the hours ticking by the clock. That's the unprimed T here. And that stretch, again, is determined by this factor here, that is determined by the speed of the platform with respect to the train. And that factor, again, we call it the Lorentz factor here, and it's 1. It would be 1 if the the platform was at rest with respect to the train, and it grows larger than 1 if the platform is moving with respect to the train. So the more the platform is moving with respect to the train, the faster it's moving with respect to the train, the more time stretches out when that observer watches the train clock. The seconds seem to get longer and longer. The hours seem to get longer and longer. And so that's time dilation. So that's one new novel effect in relativistic space-time. And here's a graph of that effect. So in this graph, I'm comparing the dilated time with the proper time. So remember, the proper time is measured by the observer where sees the clock stationary. The dilated time is measured by the observer who's seeing the clock moving. Traditionally, we call the proper time T subscript 0, naught. And we call this dilated time, we just call that T. And in this graph, I'm plotting horizontally. So this horizontal axis here, this is the speed of the observer who's moving with respect to the clock compared to the observer who's at rest with the clock. So the one that's measuring the dilated time with respect to the one that's measuring the proper time in units of speed of light, c. From 0, like that observer wasn't moving, to 1, where that observer's moving at the speed of light. And then this is the ratio of the dilated time to the true time. You see when the speed's low, right, they're the same times. The Lorentz factor is about 1. But when you get to high speeds compared to approaching the speed of light, then the dilation of time becomes a big effect. Like if you get to like about 86% of the speed of light, then that moving clock's ticking half the speed. The duration between seconds, the duration between hours is twice as long, and so on and so forth. It gets to be a very large effect at very high speeds. And so that's a change, a real fundamental change in our notions of time. Because in classical space-time, all observers agree on time intervals, but not in relativistic space-time. So the second ingredient is length contraction. And so let me show you a couple of similar slides, but now for length contraction. So now we're back in the train and the platform, and we've got our platform observer again in green here, and we got our passenger on the train observer in orange here. And now they're not going to be looking at a clock, they're going to be looking at a meter stick. And so we've got a meter stick in place of a clock here. And we got their familiar reference frame. So over here on the right bottom is the platform's reference frame, X and T. Over here on the right upstairs is the train passenger reference frame, X prime and T prime. And this is how they measured times and how they measured distances. So in this case, with the meter stick at rest on the platform, with the pedestrian observer, the platform observer measures the correct length, the proper length of the meter stick. But this observer on the train is moving through the platform with speed v. The train observer who sees a moving meter stick, the train observer measures a contracted length of the meter stick. And this equation down here describes that contraction. So the green L here and here, that's the length of the meter stick as measured by the platform observer, the green observer. with the green reference frame. The orange L prime here, that's the length measured by the observer who sees the meter stickers moving, the observer in the train. And this equation is the relationship between those two lengths, the proper length and the contracted length. And this factor here that multiplies the proper length to get the contracted length, that involves the speed, the motion of the train observer with respect to the platform observer. And that factor is actually nothing other than 1 over that Lorentz factor. So the contracted length is the proper length divided by the Lorentz factor. And remember that Lorentz factor, well, if the train was at rest in the station, then that Lorentz factor would be 1, and they'd agree on the proper length, on the length. But if that train is moving, then that length shrinks because the Lorentz factor grows beyond 1. And the faster the train moves, the more the length of the meter stick on the platform shrinks. And that's length contraction. So this is length contraction. Just like time dilation worked both ways around. You could think of a clock in the train or a clock on the platform. Length contraction also works in both directions. So this is now a picture from the perspective of the observer in the train rather than the observer in the platform. And this observer in the train here, they have their meter stick. And so the observer on the platform sees a moving meter stick. The observer in the train sees a stationary meter stick. And again, they're using their unprimed reference frame on the platform and their prime reference frame on the train to measure the length of the meter stick. And again, this is from the perspective, this picture is now really from the perspective of the train observer who's seeing the platform observer move towards the left. The length of the meter stick observed by the train observer here is the proper length because the meter stick's at rest to that observer. The length of the meter stick as observed by the platform observer, that's contracted because that platform observer is seeing the meter stick as moving. And the relationship between the two is this equation here at the bottom. So that now the L primes are the lengths in the, as measured by the train observer, with the prime reference frame where the meter stick is at rest, and that's the proper length. Those are the proper length. And the L in green, that's the length measured by the platform observer who's seeing the moving meter stick, and that's the contracted length. And again, this factor here that involves the speed of the platform observer with respect to the train observer that controls the length contraction. And that factor is nothing than 1 over the Lorentz factor. And again, as a reminder, that Lorentz factor would be 1 if the platform was at rest with respect to the train. And it grows from 1 as the platform is moving faster and faster with respect to the train. And so as the platform is moving faster and faster with respect to the train, the length would shrink and shrink and shrink. And that's length contraction. And as I say, it works both ways around, from the perspective of the meter stick of the train observer and the perspective of the meter stick of the platform observer, just like the time dilation worked both ways around, from the perspective of the clock on the platform and the clock in the train. Here's a picture of that length, or not a picture, a graph of that length contraction. So horizontally, this axis here is the relative motion of the train and platform reference frames from 0, where the train is at rest in the platform, to 1, where the train is traveling at the speed of light. So this is extremely fast. And then vertically here, on the vertical axis, that's the ratio of the contracted length to the proper length. So here's the notation we normally use for the proper length. We call it L subscript 0, like T subscript 0 for the proper time. Here's the contracted length, just L, like just T for the time dilated duration. And so this is the ratio of the contracted to the proper length, which is also equal to 1 over the Lorentz factor. And so you see at slow speeds, right, the pedestrian and the passenger basically agree on the length because the Lorentz factor is essentially 1. But at very high speeds, then they disagree on the length. And they disagree on the length according to the Lorentz factor here. Okay, let me clear that. And let's move on. And I want to move on with an example. So, but first I think, you know, those are big steps forward in our understanding of space-time. And just think about what we just did, which is what Einstein did just over 100 years ago. He tried to make the space-time landscape, the space-time fabric, the space-time background fit in with two ideas, that the laws of physics are the same for all observers, and probably that just seems fine. Why shouldn't we all agree on the laws of physics? But also that the speed of light is measured to be the same by all observers. And that doesn't seem fine. That seems against common sense, against everyday notions. But he actually went in and fixed up space-time fabric, fixed up the space-time background so that it agreed with both the invariance of laws of physics and the invariance of speed of light. And to accomplish that, he was forced to introduce time dilation and length contraction, these two new notions that the time interval between two events is not the same for all observers. It depends on your motion with respect to those events, like the ticks of a clock. And the length of an object is not measured to be the same for all observers. It depends on your motion with respect to that object. So different observers moving with respect to the meter stick in different ways measure different lengths. So those are fundamental ingredients. And now I want to look at an example, an illustration of time dilation and length contraction. Now we've introduced it. And so let's start with the statement here. We're told that an astronaut travels I think this is meant to be 4.2. 4.2 light years from Earth to the nearest star. The nearest star is Alpha Centauri. And they travel that distance at 95% of the speed of light, 0.95 times c. And so we're just told this trip, right? I even drew a picture of the trip. Look, here's the trip. Astronaut starts on Earth. That's kind of the departure event. Astronaut travels to Alpha Centauri. This is the solar system. It's the closest star in our solar system. No, it's not the solar system. It's our galaxy, the Milky Way. It's the closest star in our galaxy. So that's the arrival event when astronaut gets there. And here's the trip. Here's the astronaut and the trip in the spacecraft traveling at 95% of the speed of light, 0.95 of the speed of light. There's a couple of questions here. First one is find the time measured by the astronaut, and she's in the spaceship for the trip, and the time measured by her spouse, who's at home for the trip. So imagine my spouse is an astronaut, and she's gone away on a trip. I mean, I sometimes go away on trips, and she's gone away on a trip, and she's going to Alpha Centauri. And she's going to measure how long she thinks she's away, and I'm going to measure how long I think she's away. And she'll be measuring how long she's away with the clock in the spaceship, obviously, and I'll be measuring how long I think she's away by the clock as I sit in the house, the clock in the house. So that's one question. So we're going to answer that. We'll answer that first. And then here's the second question. Find the distance measured by the astronaut in a spaceship to Alpha Centauri, and find the distance that I measured as the spouse for the length of a distance of a trip to Alpha Centauri. So find the two distances. So these are questions really about, as you can imagine, about dilated and proper times and dilated and proper lengths. And we've really got to understand who are the dilated times and contracted lengths, and who are the proper times and lengths to work this problem out correctly. And so let's see if we can do that. Before I do it, though, I just want to mention the fact I quoted the distance from Earth to Alpha Centauri as 4.2 light years. And this is an important point for this problem. I better explain. A light year is a distance, first of all. Sounds like a time, but it's not a time. It's actually a distance. A light year is the distance that light travels, the number of meters that light travels in one complete year. One complete year is 31 million seconds, roughly. So that's what a light year means. You know, we don't use light years for everyday distances. You know, if you were going to Louisville or you're going to New York, you're not going to say how many light years it is. But if you were traveling astronomical distances, then you would use light years because it's a much more natural length scale. So it's 4.2 light years to Alpha Centauri from our solar system. And so that's why I marked this picture up like this. We've been told this distance between Earth, or the solar system over here on the left, and Alpha Centauri over here on the right. That's 4.2 light years. And actually, it's an important point here. We've been told the proper distance. So, you know, Earth is out there floating in space. Alpha Centauri is floating in space. And this is the proper distance between them. They're just sitting there. And we're being told it's like measured from the perspective of Earth, an observer on Earth, measured from the perspective of an observer in Alpha Centauri. This is how far apart these two locations are. So this is actually a proper distance. And just to make you believe that a light year is a distance, I calculated that a 1 light year in meters. So 1 light year, we often write it like this: c, light speed times year. Light speed is 3 times 10 to the 8 meters per second. 1 year is 31 million seconds. If I look at the units, I've got seconds in the denominator and seconds in the numerator, so those go away. I'm left with just units of meters. If I multiply the two numbers, a light year is about 9 times 10 to the 15 meters. So it's a huge number of meters. That's 9 times 10 to the 12 trillion kilometers. It's about 6 trillion miles, just to give you an idea. So that is a distance. Okay, so I want to make some comments before I solve the problem about proper times, dilated times, about proper lengths, dilated lengths, and about speeds in this problem. So firstly, let's start with speeds. That's this guy here. So we were told that the astronauts traveling 0.9, 95% of the speed of light. So in the Earth reference frame, my reference as the spouse, my reference frame, I'm seeing the astronauts and the astronaut reference frame travel at 95% of the speed of light towards the right. And also in astronaut reference frame, the astronaut seeing me in the Earth reference frame is traveling at 95% of the speed of light towards the left. So that's important. The two reference frames, Earth reference frame and spaceship reference frame, are traveling at 95% of the speed of light with respect to each other. And the gamma factor, the Lorentz factor, if you calculate it, remember it's the square root of 1 minus v squared over c squared, 1 over that. That's 3.2. And so that's an important factor in this problem. Okay, so that's a comment about the Lorentz factor and the speeds. Second comment is related to times. So who's seeing the proper time for the trip and who's seeing the dilated time? So that's an interesting question. It's actually the astronaut that sees the proper time, and it's the spouse, me stuck on Earth as usual, who sees the dilated time. So the astronaut sees the proper time because the proper time is measured by the clock where the departure and the arrival, the departure Earth and the arrival at Alpha Centauri are at the same location. Well, that reference frame that sees the departure and the arrival at the same location, that's the astronaut's reference frame. So if you think about the reference frame blocked to the spaceship, then the departure from Earth and the arrival at Alpha Centauri are occurring at the same location. They're occurring at the location of the spaceship. And so that clock that's in the spaceship gives the proper time for the trip. And so that's important. And the spouse will see the dilated time for the trip. When the spouse sees how much time, measures how much time has passed for that trip, they're going to see the dilated time. So they're going to see a longer time. I'm going to see a longer time. What about the proper length for the trip and the contracted length for the trip? Well, in this case, the spouse measures the proper length and the astronaut measures the contracted length. In this case, right, the spouse is on Earth. I'm sitting back in the house. I'm just waiting for my astronaut spouse to return. I'm sitting there and, I'm at rest in the Earth Alpha Centauri reference frame. And so I'm going to measure the proper length between those two places, the proper distance between those two places. The astronaut spouse is moving with respect to the Earth and Alpha Centauri. Has to be to get there, to make the trip. And so they're going to see the contracted length. And so that's an important thing, that the spouse is measuring, the earthling is measuring the proper length, and the astronaut is measuring the contracted length. And so now we've figured that out. Now we know who owns the proper time, who owns the contracted time, who owns the proper length, who owns the contracted length. We can figure out the various times and the various lengths. So let's do that. That's the next slide. The dilated time. Okay, so the dilated time is the one that the spouse sees, as I explained on the last slide. The proper time is the one that the astronaut sees. So this is the dilated time that we're going to calculate here, and this is the proper time for the astronaut that we're going to calculate down here. So the dilated time, to figure out the dilated time, let's just use the relationship between the distance traveled, the time taken, and the speed. So that's just something that we met in Physics 211, the relation between speed, distance traveled, and elapsed time. And the speed is the distance traveled by the elapsed time, or the time taken is the distance traveled divided by the speed. So the distance traveled, as seen by the spouse, is the proper length, and the speed is the speed of the astronaut. And so I've just got to divide the proper length between Earth and Alpha Centauri by the speed that the astronaut's traveling at. And so I've got to divide the 4.2 by the 0.95. That gives me 4.53. And then I've got to, the units will be, well, the C's are cancel out, and I'll just be left with the units of years. So I'm the spouse. I'm measuring the astronaut taking 4.53 years to get to Alpha Centauri. What about the astronaut? How long do they measure? Well, look, this is the relationship here between the proper time on the right and the dilated time on the left. If I rearrange that, because I don't know the proper time, I know the dilated time now. If I rearrange it, the true proper time is the dilated time divided by the Lorentz factor. So all I got to do is take the spouse's time and divide it by the Lorentz factor, and that's the proper time. So the astronaut measures 1.38 years. So this is the proper time for the trip. It's where departure and arrival occurred at the same place. This is the dilated time for the trip. This is the longer time. Look, I'm the spouse on Earth. I'm going to say it took you way longer to get there than you said it was going to take. And so that is the dilated time. Okay, what about the second half of the problem? Here we are. The proper length or proper distance for the trip and the contracted length. So as we said, I'm the spouse here, and I've measured, and we were told in the problem, the proper length. So the proper length is the one where Earth, proper distance is the one where Earth and the spaceship, Earth and Alpha Centauri are at rest. And that was 4.2 light years. And I even calculated it in meters here by multiplying this conversion factor between light years and light years and meters. The astronaut will measure the contracted length because they're moving with respect to the Earth and Alpha Centauri. They're moving with respect to that distance between Earth and Alpha Centauri. So this is the equation for length contraction. We just got to take the proper length and divide it by the Lorentz factor. So the astronaut thinks that there's only 1.31 light years between the Earth and Alpha Centauri. So they see a reduced, the contracted length between those two places. Okay. Okay, so I had a quiz, but I'm really run out of time for the quiz. So I'm going to give everybody, I messed up. I already published the quiz. I'll just give everybody credit for the quiz. And so I'll do that. Let me just summarize, though, that today's class has been about the foundations of relativity. And there are two foundations, as I say. One is the invariance of laws of physics. That seems common sense. The second one is that the speed of light is invariant for all observers. That doesn't seem like common sense. For those two things to be true, Albert Einstein had to fix up space-time, had to change our notions of space-time. What he did was introduce the relativity of durations, time intervals between events, and that's time dilation. And he also introduced relativity of the lengths of objects. That's length contraction. We talked about that. And there's one other thing he introduced, I'll just mention this, is that we don't agree on simultaneity. One observer may say that two events are simultaneous, and another observer in a different frame might disagree that they're simultaneous. So those are the three sort of big outcomes of Einstein's modification of space-time. What we're going to do in the next class, just to show you this last slide, if I can, is we're going to worry about the following. We've just changed our notions of space-time, just changed our space-time fabric or the space-time background. And look, here's Isaac Newton. He's worried because he invented these laws that describe how forces act and change the motion of objects through space and time, and how forces transfer energy and momentum by acting in space-time. But if we change the space-time fabric, have we ordered how the laws of motion work? And so we're gonna look at that in the next class. That'll be our second class on relativity.